the final value theorem. If we have some dependent variable f, we can know what happens to it in the time domain as time goes to infinity by analyzing what's happening in the frequency domain. So if we first look at the actual final value theorem, what it tells us is, as t goes to infinity of f of t, this is our variable in the time domain, it's going to be the same as if we take s times f of s, where f of s is the Laplace transform of that variable, so s times that, but take the limit as s goes to 0. So notice a couple things here, and we'll see parallels in the initial value theorem. In the time domain, we're going to infinity, but in the frequency domain, we're taking the limit as s goes to 0. So infinity versus 0. We're going to see that flips in the next part. And we're taking the limit as s goes to 0 of s times f of s, not f of s itself. And this will tell us what happens to our function in the time domain for large time. So this tells us what we call the steady state value of f. Now, before we can apply the theorem here that's in green, if we have our f of s, we do have some restrictions on this. When is this going to be true? And this is above. So we have to look at all the poles of s times f of s. And we have a keyword here of poles. S times f of s is usually going to be a fraction, where we're going to have a polynomial in s on the top and a polynomial in s on the bottom, in the numerator and the denominator, that is to say. So what we're looking for is s times f of s. What are the poles of that fraction? The poles are going to be the values of s that make the denominator equal to 0. This is in contrast to what we're going to be calling zeros, which are the values of s that make the numerator 0. Depending on the degree of the polynomial in the numerator and the denominator is going to tell us how many poles we're going to have from the denominator, the same as the degree, and how many zeros based on the degree of the numerator we're going to have. So we need to have all the poles of s times f of s lie in the left half plane. So again, another key word here, what's the left half plane? The poles could be real, they could be imaginary, or they could be complex. The left half plane is indicating that whatever the values are, that the real part is strictly negative. So thinking of the real imaginary coordinate system, the left half plane, the real part is strictly negative. So actually this rule is a little bit stricter than what the actual rule is, where you could actually have one of the poles at 0. We're going to be a little bit stricter for this course in how we apply final value theorem and say that they all must be in the left half plane. They all must have strictly negative real parts. And what this tells us, if all the poles have strictly negative real parts, if they're strictly in the left half plane, that tells us that our variable is stable, which is to say that our variable, given enough time, is going to go to a constant value in the time domain. All right, so to use this, and the same is going to be true for initial value theorem, first we must show that we have a stable system. That is to say that this is true based on the poles of s times f of s. Then we can apply the theorem in green. So let's go through a quick, what I'll call informal proof, not using the strictest mathematical rules here, but I just want to prove that the statement or this theorem in green is going to be the case. So if I take my f dot of t, so that is just the time derivative of some function f. If I take the Laplace transform of it, I have two definitions. I have that strict calculus definition that we started with when talking about Laplace transforms. So this is the actual definition of a Laplace transform. I take the thing inside the Laplace transform, and I'm going to multiply it by e to the negative st, and I integrate it from 0 to infinity. So that's the literal definition of what the Laplace transform does. And I know from the Laplace transform table that the Laplace transform of f dot of t is going to be s times big F of s minus f of 0. So that is going to be the case for any the derivative of any dependent variable. That's what we have from the Laplace transform table. So let me take this middle part, this integral, and what I'm going to do is I'm going to take the limit as s goes to 0 of that integral, and I want to see what happens to it. Right, so I am going to let s go to 0. And if I see what happens, well, if s goes to 0, then I have e to the 0. E to the 0 is just going to be 1. And I'm going to be left with then just the integral from 0 to infinity of f dot of t. And now that limit goes away because I have no more s terms. The limit's not going to affect anything else. And informally, this is where it's not quite mathematically the most rigorous proof here. The integral is going to be the antiderivative of the thing inside, evaluated at the upper limit, minus the antiderivative of the stuff on the inside, evaluated at the lower limit. So the antiderivative of f dot is just f. So this is going to be f of infinity minus f of 0. Again, I really can't do that for a infinite integral like we have here, but relaxing the math rules a little bit, this is roughly going to be true. All right, and now if I put this aside for the moment, I want to take the limit as s goes to 0 of this term here, this s f of s minus f of 0. Right, so here, if I put in, I know that that's going to be equal to the limit as s goes to 0 of the integral term, and that's what I just found the value of, this f infinity minus f 0. So now I can go forward a little bit here. If I simplify, I have this f naught, and I have this f naught, or f of 0 and f of 0 on both sides, so those are going to cancel each other out. And then what I'll be left with is this limit as s goes to 0 of s f of s on the left-hand side. I can't simply substitute s as 0 here because I don't know what the f of s is doing. It's possible that the f of s is growing faster than s is getting smaller, so I have to leave that as a limit. And on the right-hand side, I have this f of infinity. So a little bit more formally now, I'm going to switch the sides of everything. Instead of leaving it as f infinity, I'll use the more proper limit as t goes to infinity of f of t equals what I have left on this left-hand side. Again, I'm just writing that over there, and this term I am writing on the left-hand side. So what I have left is the limit as s goes to 0 of s times f of s. And what we see then is that through this pretty quick informal proof, we have shown exactly the same thing that we had in green above, which is the final value theorem.